Hello everyone, welcome to our YouTube channel. This video is presented by Likita Baratam and
Jyoti Dasari
under the guidance of Dr. M. Prasad sir, PhD, Associate Professor.
and the Department of CSC, Sri Vishnu Engineering College for Women, Bhimvaram.
And then our topic is classic problems of synchronization. And then these are the topics we are going to be discuss in this video. They are synchronization, deadlock, starvation, race condition, and the classic problems of synchronization, etc. Firstly, what is meant by synchronization? Synchronization refers to the coordination of multiple processes or threads to ensure orderly execution. Process synchronization is the coordination of execution of multiple processes in a multi-process system to ensure that they access shared resources in a controlled and predictable manner. It aims to resolve the problem of race condition and other synchronization issues in a concurrent system. The main object of process synchronization is to ensure that multiple processes access shared resources without interfering with each other and to prevent the possibility of inconsistent data due to concurrent access. To achieve this, various synchronization techniques such as semaphores, monitors, and critical sections are used. In a multi-process system, the synchronization is necessary to ensure data consistency and integrity and to avoid the risk condition of deadlocks and other synchronization problems. Process synchronization is an important aspect of modern operating systems and it plays a crucial role in ensuring the correct and efficient functioning of multi-process systems. Then next, deadlock. What is deadlock and what is meant by deadlock? Deadlock is a situation when two or more processes are unable to proceed because each is waiting for other to release a resource, like seen as in the picture. It can occur when process complete for finite resources and each process holds one resource while waiting for another. Deadlock can lead to a system freeze and requires careful handling to prevent or resolve. This is the picture which shows deadlock condition. Then the next one is starvation. What is meant by starvation? Starvation occurs when a process is perpetually denied access to resources it needs for execution. It can happen when resources are allocated unfairly, leading to some process being consistently prioritized over others. Starvation can result in reduced system performance and fairness issues. Then, deadlock versus starvation. Which is better? Starvation occurs when a process waits for a resource that becomes available continuously but is not allocated to a process. The mainly two main differences are there in between deadlock and starvation. In starvation, it is not set time that a process will ever get the requested resource, whereas a deadlock process is permanently blocked because required resource never become available. In starvation, the resource under contention is in continuation use, whereas this is not true in case of deadlock. Then, race condition. What is meant by race condition? When one or more than process is executing the same code or accessing the same memory or shared variable in that condition, there is a possibility that the output or the value of the shared variable is wrong. So, for that, all the processes during the race to say that my output is correct. This condition is known as race condition. Several processes access and process the manipulations over the same data concurrently, and then the outcome depends on the particular order in which the access takes place. A race condition is a situation that may occur inside a critical section. This happens when the result of multiple thread execution in the critical section differs according to the order in which the threads execute. Race condition in critical section can be avoided if the critical section is treated as an atomic instruction. Also, proper thread synchronization using lock or atomic variables can prevent race conditions. A race condition occurs when the behavior of a program depends on the relative timing of events. It happens when multiple threads or process access shared data concurrently without proper synchronization. Race condition can lead to unexpected and non-deterministic outcomes, making the program difficult to debug.
And the next one is critical section. A critical section is a source segment that can be accessed by only one process at a time. The critical section contains shared variables that need not to be synchronized to be maintained that consistency of the data variable. So the critical section problem means designing a way of cooperative processes to access shared resources without creating data inconsistency. In the entry section, the process requires for entry in the critical section. Any solution to the critical section problem must be satisfied in three requirements. Here the picture represents source code of critical section. The first condition is mutual exclusion, and the next progress, and the next bounded waiting. First, we see the mutual exclusion. If a process is executing in its critical situation, then no other process is allowed to be execute in the critical section. And the next is progress. If no process is executing in the critical section and other process are waiting outside the critical section, then only those processes that are not executing in their reminder section can participate in deciding which will never the critical section next, and the selection cannot be postponed indefinitely. And the next one is bounded waiting. A bound must exit on the number of times that the other processes are allowed to enter the critical section after a process has made a request to enter its critical section and before that request is generated. Producer and consumer problem. The producer and consumer problem involves into processes. A producer that can produce data and a consumer that can consume data. The challenges is to ensure that the consumer does not consume data that has not been produced yet and vice versa. Synchronization mechanisms like semaphores or monitors are used to solve this problem. Here is a picture that represents the producer and consumer problems. And the next one is readers writers problem. The readers writers problem involves multiple readers and writers accessing a shared resource such as file or database. Readers do not modify the resource while writers both read and modify it. And the next point is the challenges is to allow concurrent reading while ensuring exclusive access for writing maintained data consistently. And the next one is dining philosopher's problem. The dining philosopher's problem illustrates resources allocation and deadlock avoidance. In this problem, philosophers sit at a table and alternate between things and eating. They share chopsticks, and the challenges is to prevent deadlock. When all philosophers pick up their left chopsticks simultaneously. Here is the picture that explains the dining philosopher problem. And the next one is sleeping barber problem. The sleeping barber problem represents a synchronize where customer arrive at a barber shop and either wait or walk up the barber. The challenges is to ensure that the barber does not cut hair. If there are no customers and customers don't wait indefinitely if the barber is busy. Your tied third bullet. Here is a picture that explains about the sleepers barber problem. And the next one is bounded buffer problem. The bounded buffer problem involves a buffer with a limited capacity and multiple producers and consumers. The challenge is to ensure that producers does not produce. If the barber is full and the customer does not consume, if the barber is empty. And the next point is semaphores or monitors can be used to solve this problem.
And the next topic is critical section problem. The critical section problem focuses on ensuring that only one process or thread access a critical section of code at a time. It involves mutual exclusion to prevent race conditions and ensure data integrity. The critical section problem is used to prevent race conditions and ensure data integrity. Synchronization primitive like locks, semaphores, or monitors are used to solve this problem. Two-phase locking. Two-phase locking is a concurrency control technique. It is a technique used to ensure serializability and avoid conflicts between transactions. It consists of an acquiring phase where locks on resources are acquired and a releasing phase where locks are released. Two-phase locking helps prevent race conditions and maintain data integrity. Here we have the two-phasing locking protocol. This is a protocol which ensures conflict serializable schedules. In this we have two phases. In phase 1, growing phase, phase 2 is shrinking phase. In growing phase that may have transaction may obtain locks, transaction may not release locks. In phase 2 they have transaction may release locks, transaction may not obtain locks. The protocol ensures serializability. It can be proved that the transactions can be serialized in the order of their lock points. That is, the point where a transaction acquired its final lock. This is the diagram of two-phase locking protocol. The next, lastly, I will conclude that classic problem of synchronization such as deadlock, starvation, and race conditions are common in concurrent programming and operating systems. Solving these problems requires careful design and implementation of synchronization mechanisms. Understanding and addressing these problems are essential for building reliable and efficient concurrent systems. Thank you.